So, what do your smartphone, a burning star way out in the distant cosmos, and your own living, breathing body actually have in common? I know, it kind of sounds like the setup to a weird riddle, right? But the answer is literally the foundation of everything we can see, touch, or interact with. Because believe it or not, they are all built from the exact same fundamental building blocks.
Welcome to this explainer. Today, we are taking a fresh look at something you probably remember as just a really complicated wall chart from your high school science class. But we're going to see it for what it truly is. The ultimate, honestly fascinating, recipe book for our entire universe. Yep, I'm talking about the periodic table of elements, because truly understanding this table means understanding exactly how matter behaves and why different substances do what they do. All right, let's just dive right in. Here's our roadmap for today. First, we'll meet your building blocks. Then we'll be decoding the table, comparing metals versus nonmetals, exploring elemental families, and finally, looking at elements in everyday life.
So, Section 1. Meet your building blocks, the anatomy of an atom. You know, absolutely everything around us is made of atoms. And by definition, an atom is the absolute smallest unit of an element that still actually retains that element's unique properties. Basically, you can't break it down any further using ordinary chemical reactions without entirely losing what makes it special in the first place.
Now, what's really cool here is what happens when we crack that atom open and take a look inside. Every single atom consists of three main subatomic particles. First up, we've got protons. These carry a positive charge and sit right smack in the middle, inside the nucleus. And protons are absolutely crucial because they actually determine the identity of the element. Like hydrogen always has 1, carbon always has 6. No two different elements will ever have the same number of protons. Second, we have neutrons. These are also hanging out in the nucleus, but they have a neutral charge. They're mostly there to help stabilize the nucleus and add a bit of mass. And third, the electrons. These have a negative charge and they just zip around the nucleus in these specific energy levels. And usually the number of protons perfectly equals the number of electrons, which makes the whole atom electrically neutral.
Moving on to Section 2. Decoding the table. Making sense of the elements.
So how in the world do scientists actually organize all these tiny atoms? Well, so far they've discovered over 100 unique elements. To put that into perspective, imagine having over 100 completely different, fundamental ingredients sitting in your kitchen, and you need to organize them in a way that actually makes logical sense. That is exactly what the periodic table does for us. The secret to pulling off this massive organizational feat is the atomic number. Think of it as the element's ultimate ID badge. This number perfectly matches the number of protons we just talked about. So hydrogen's atomic number is 1, meaning it has 1 proton. Helium is 2, so it has 2 protons. Carbon is 6, so you guessed it, 6 protons. The periodic table just elegantly arranges all known elements by this increasing atomic number. And this brilliantly illustrates how the whole grid layout actually works. I promise, it's not just a bunch of random boxes. Horizontally, we have 7 rows, and these are called periods. As you move from left to right across a period, the atomic number goes up and the properties of the elements gradually shift. But vertically, we have 18 columns called groups, or sometimes families. Elements in the same group actually share chemical properties, and that's because they have the exact same number of outer or valence electrons. For instance, lithium, sodium, and potassium are all in the exact same group, and they will all react violently if you drop them in water. Why? Because they each have just one solitary outer electron.
Now, when we talk about the properties of these elements, we're really talking about two different things. Physical properties are the things we can observe without actually changing the substance itself, like its color, its density, its melting point, or how hard it is. Chemical properties, on the other hand, describe how an element actually reacts with something else. Think of processes like rusting, burning, or corrosion.
All right, Section 3, metals versus nonmetals, categorizing the table.
So, if you look at the whole table, the vast majority of elements are actually metals. You know these. They're generally shiny, malleable, ductile, and they are fantastic conductors of both heat and electricity. We're talking about things like gold, iron, or copper wire. But on the flip side, we have the nonmetals, and these are basically the exact opposites. They are really poor conductors, they tend to have a pretty dull appearance, and if they happen to be solid, they're super brittle. Interestingly though, a lot of them, like oxygen and nitrogen, are actually gases at room temperature. But what happens right there in the middle? Well, we get metalloids. These act as this really vital bridge between the metals and the nonmetals. They basically have intermediate properties, which happens to make them incredible semiconductors.
Elements like silicon and germanium sit right in this sweet spot. And honestly, without them, you literally wouldn't have modern computers, solar panels, or that smartphone you carry around in your pocket.
It's also really worth noting the physical states these materials can actually take on. You probably know this, but matter exists in three common states. First, solid, where the particles are packed tightly together, giving it a definite shape and volume, just like a chunk of iron. Then there's liquid, where particles are close together but still fluid, giving it a definite volume but no fixed shape. Though fun fact here, only two elements on the entire periodic table, mercury and bromine, are naturally liquid at room temperature. And finally, gas, where the particles are spread far apart, zipping around rapidly with absolutely no fixed shape or volume, like oxygen.
Which brings us to Section 4, Elemental Families, the Character Profiles.
Let's take a quick tour of a few standout families on the table. Over in Group 1, we have the alkali metals. These are so incredibly reactive that they will fiercely explode if they touch water. You literally never find them just sitting alone in nature. Then Group 2 gives us the alkaline earth metals. They're still reactive, but harder. Think of calcium, which literally physically builds and strengthens your bones. Right there in the middle, spanning Groups 3 through 12, are the transition metals. These are the strong, good conductors like iron and copper that we use to build massive bridges and intricate jewelry. And over on the far right side in Group 17, we have the halogens. These are highly reactive nonmetals, like chlorine, which we heavily rely on for things like water purification.
I also want to take a quick look at Group 15, the nitrogen family. The numbers here are honestly staggering. Nitrogen alone makes up roughly 78% of Earth's atmosphere. So right now, when you take a deep breath, the vast majority of what is filling your lungs belongs to this one specific elemental family.
And that brings us all the way to the right edge, Group 18, the noble gases. Now, if you happen to be reading through some older science materials, or maybe some messy class notes, you might sometimes come across a statement exactly like this one. Noble gases are very reactive gases.
But I want to stop right there and just correct the record for a second. That is completely 100% incorrect. Actually, noble gases, think of things like helium, neon, and argon, are incredibly stable and completely unreactive. Remember earlier how we said elements react based on the number of their outer electrons? Well, a noble gas's outer electron shell is totally, completely full. They literally have no need to react with anything else, and that's exactly why they're called noble. They much prefer to just stand entirely on their own.
All right, final section, Section 5, Elements in Everyday Life, the Macro Scale.
So zooming way out, how do all these tiny atoms and families actually build the big macro world we interact with every single day? Well, this really brings it all home. Carbon forms the fundamental basis of all living organisms, and yep, that includes you. Silicon is the absolute foundation of our computers and smartphones. Copper makes up the electrical wiring that's running through your walls right now. Aluminum gives us our everyday foil in soda cans. You see, it's not just some abstract science concept. These pure elements are the literal, physical materials of human civilization.
And it gets even crazier when you see what happens when we start combining them. It's like pure magic. You take hydrogen, add some oxygen, and boom, you get to water we drink every day. You take sodium, which is a highly explosive metal, and combine it with chlorine, a literally toxic gas, and they perfectly bond to form completely harmless, delicious table salt for your dinner. Oxygen allows us to respire and stay alive, while totally unreactive helium gives us those fun floating party balloons.
We've seen how everything, starting from the absolute smallest atom with its tiny protons, neutrons, and electrons, perfectly organizes into this beautiful, intricate map we call the periodic table. It literally dictates whether something is going to be a solid, a flowing liquid, a shiny metal, or a highly reactive gas. So I want to leave you with this one final thought. The next time you look around your room, try to look past the everyday objects themselves. Ask yourself, which of the 100+ elemental recipes are you actually looking at? Thanks so much for joining me on this explainer, and keep exploring the incredible building blocks of our universe.